Good day. Today, I will solve an electrodynamics problem. It's a Laplace equation problem, and the problem is given the title, the semi-infinite rectangle. Okay, and the geometry I'm going to sketch here briefly. Well, that was supposed to be straight. I didn't succeed. That's the y-axis. That's the x-axis. And this is x equals a. Okay, and let me actually try to indicate what's going on here. So this is our arrangement. So we have a plate here at x equals a, going from 0 to infinity in y. We have a plate here at x equals 0, going from 0 to infinity in y. And both of these plates are capped at the potential of 0. And this plate, this bottom plate, connects them from x equals 0 to a, and it is kept at the potential of V0. Okay, and our task is to find the potential of this arrangement. Okay, so I'm going to just write a potential, and the first thing I will do is consider the boundary conditions. So I'm going to write down the boundary conditions explicitly. Okay, so you can say phi 0 and y is equal to 0. That's one boundary condition. You also have phi a y is equal to 0. So that's this one and this one. And then we also have phi x 0. And this is where the potential is kept constant. We actually have another boundary condition which we should not forget about, namely that phi x as y goes to infinity. So this that's a limit that should go to 0 also. Okay, so this is our basic problem, and we are to solve for the potential in that region, okay, that I shaded there, and we're going to do it by solving the Laplace equation, which I can write explicitly as in terms of the second derivatives. It's maybe a little bit too detailed, but okay, so that's actually what we are after. And the first step that we're going to do, okay, so the first step in solving this problem is that we apply what is called the separation of variables. Okay, so we have phi x, y, and we're going to write that as the product of one function, which is only a function of x, and another function, which is only a function of y. Okay, so that's our starting point. And then when we substitute that into the Laplace equation, okay, so we're going to have, so actually, sorry, that was boundary conditions. I indicated that. And this, I didn't call it anything. I didn't write it explicit, but this is the Laplace equation. Because that's this one or this one. Both of these are Laplace. Okay, and now I put this into the Laplace equation. I'm going to get y of y partial squared x partial x squared. The first term only has an x derivative, so it doesn't affect the y at all. And then the second term is going to be like this. That's equal to 0. Okay, and then what I'm going to do is I'm going to divide by the solution again. Okay, so that's going to give us 1 over x of x partial big X with respect to x squared. So second derivative plus 1 over y of y and second derivative with respect to y, and that's equal to 0. And now the interesting thing to note is that this here is only a function of x, and this here is only a function of y. Okay, so we can actually take them to be constants, so to speak, with respect to each other. Okay, and they are constants, and they have to actually, yeah, this is the point here. So this term here doesn't depend on x, right? So that means that this term altogether is actually a constant. And this term here doesn't depend on y. This term here is also a constant. So these two constants, however, have to sum to 0, because that's our Laplace equation. So I'm going to take this constant to be minus alpha and this constant to be alpha. So I have now two new equations, which look like 1 over big X of x, x of x minus alpha, and 1 over y of y. This is equal to plus alpha. Okay, now actually it's a little bit arbitrary what I did here, because I chose this to be minus and plus. It will be obvious why that's actually a convenient choice shortly. Okay, so now we need a function x whose second derivative divided by the function itself gives us a constant. Okay, and there aren't too many functions like that, but it's actually the trigonometric functions which satisfy that condition. If I go back to my original geometry, so here we're talking about the function which in the x direction, and we see that it has to go from 0 at x equals 0, and it has to go back to 0 by the time it gets to x equals a, meaning that it's convenient to take this to be a sine function. Okay, so in this case, alpha is going to be k squared. Okay, a sine is an oscillatory function, so if it starts at 0, it goes back to 0 at some point. But if you look at this, it has to start at x equals 0 and go back to 0 at x equals 0. So that actually tells us that k should be of this form, m pi divided by a. Okay, so so we're starting to put the solution together. Now, what about this one? This one actually is again a constant, second derivative of the function divided by the function itself. It has to give you a positive constant. Well, not many functions do that either. Sorry, I'm pushing this up. So what I found here is alpha equals k squared. Not many functions do this either. So y of y is equal to e to the minus m pi over a times y. Okay, so if I take this to be the solution for big X and this to be the solution for big Y, I'm going to be okay. So actually, for example, if you take as the solution of your potential sine m pi x over a e to the minus m pi over a y, okay, that actually satisfies the Laplace equation. Okay, so either one is going to satisfy this Laplace equation. However, so n is an integer. Okay, so this boundary condition, I forgot to say that, but m is 1, 2, etc. It's an integer, because m can be any integer. And since if you have two solutions of the Laplace equation, second order differential equation, then the sum of those two solutions will also be a solution. And that goes for the whole sequence. Okay, so actually the most general solution that we can write is m sine m pi x over a e to the minus m pi y over a. Okay, so that's the general solution that we can write at this point, armed with what we are finding of the trigonometric function in one direction and the exponential decay function in the other direction. Let me actually just briefly try to draw this. I'm going to try to attempt a three-dimensional drawing. So this is going to be my phi, okay? This might be my x. Let's say this is going to be my y, okay? And basically what we're going to have, this is x equals a. This here is x equals 0. So we're going to have maybe for m equals 1, say, you have a sine curve which decays exponentially. So it's something like this, okay? But m is not only 1, okay? So it's all the other ones too. So that, but that's the idea. Okay, now we want to actually determine what these coefficients are. That's our next step. And for that, we have to use the fourth boundary conditions, which we haven't used yet. Let me actually just remind you that we used this boundary condition and this one because the sine satisfies that. We used this boundary condition because the exponential decay satisfies that. This one we have not used yet. Okay, so let's do that. And that's going to help us fix these coefficients. Okay, and what we're going to do is the Fourier trick, which is based on the idea of orthogonal functions. Okay, so, and sine m pi x is definitely an orthogonal function. Okay, so now we are using another boundary condition, so we can say that f phi x0 is equal to v0, okay, which means m equals 1 through infinity sine m pi x over a okay, so that's actually our so this sequence has to give us this v0, okay? And the orthogonal function trick is to take the function 0 to the orthogonal function, which is the sine in this case. So I'm going to take sine n pi x over a and take once the left side of the equation, which is v0, and put it here and do this integral. And also the right side of this integral, which is this mess here, and put it here and perform the integral. So I'm actually do the left side first. So 0 to a, that's v0, I can pull that out of the integral, sine n pi x over a dx. Well, that's going to be v0 a over n pi negative cosine n pi x over a, and the limits on this are of course 0 and a, okay? And we have to now substitute the limits, so that's going to be v0a over n pi. Okay, the upper limit is minus cosine n pi once I substitute that a, and the lower limit is actually plus 1, okay, so that's just 0. And now this is actually, so this cosine n pi, of course, is minus 1 for n odd and 1 for n even. Okay, so we can write this in another form, which is v0a over n pi. We can write it as minus 1 to the n minus 1 to the n plus 1. We can also write this as 2v0a over n pi for n odd and 0 for n even. Okay, so we determined the left hand side of this integral. Now we determine the right hand side. Okay, and then we put them together. So for the right hand side, we're going to have, well, 0 to a sine n pi x over a, and then I put here m equals 1 through infinity am sine n pi x over a dx. Okay, sorry, actually this is an m. Okay, and the important integral here is this one, sine n pi x over a sine m pi x over a dx. And Well, this is the particularity of orthogonal functions, that this is actually proportional to a delta function. In other words, if m is not equal to n, then this integral is 0. Okay, but I'm not finished yet. We also have to evaluate it for m equals n, in which case you have to do the integral sine squared n pi x over a dx, right? And that's actually not too bad, right? Because you're guaranteed that this is going to be half a period or a full period. Okay, half a period if n is odd, or a half odd period. So it's going to be something like, this or this or this, but it's squared. Okay, so it's squared. So it's not that, actually. That's the sine function. Here's a. So it's something like this, and it's like this, or like this. Okay, and so basically, you can say that you can easily show that this ends up being the length a divided by 2. Okay, so it's you can see that because this all of these integrals. So let's just take n equals 1. Okay, we don't have to really do this, but okay. So I have this one, which is sine squared pi x over a. Okay, if I shift this, okay, so if I shift it, then I get cosine, and it's obvious that these should give the same contribution. Okay, and if I add cosine squared plus sine squared, I get 1. So if I add cosine squared n pi x over a plus sine squared n pi x over a dx, then I should actually get a, because sine squared plus cosine squared, sine squared plus cosine squared is 1. Okay, now I'm sort of using n equals 1 as an example, but it holds for all the others. And it's obvious that this integral and this integral should be equal. So this has to be a over 2. So actually we're home. Here I put an a over 2 to finish this, which means that this integral here ends up being a n small a over 2. Okay, and based on our previous result, now we can put together that the so on one side of the equation I had a and a over 2, and the other this what I actually got, right? So I can say that if I put those together, that an is 4v0 over n pi for n odd, and 0 for n even. Yeah. Okay, so I can write my full solution phi xy as n1 through infinity, and I guess I can write it as 4v0 over n pi sine n pi x over a e to the minus n pi y over a, but I have to be careful that this is, I should indicate that those are just only the odd terms in the sum. Okay, and now there's actually still something we can do. This is actually, we can actually perform the summation, interestingly. Okay, so that's actually something interesting that I will just do here. You know that e to the ix is cosine x plus I sine x. Okay, so, and sine x in general is the imaginary part of e to the ix. Let me actually just not confuse, let me call this x tilde, so that we don't confuse it with this x, because this is just a generic argument here. E to the ix tilde is cosine x tilde plus I sine x tilde. So we can actually write phi xy as, let's pull out the 4v0 divided by pi. And I'm going to write here that it's the imaginary part of n equals 1 through infinity. These are still just the odd terms. E to the I n pi x over a and e to the minus n pi y over a. And it's still divided by n, okay, because I'm not able to pull that out of the sum. And now we're going to define a variable, which is going to be e to the minus n pi y over a, e to the plus I n pi x over a. Okay, and we're just going to play with this sum. Okay, so I'm going to say define a function fz, which is z to the n divided by n. That's a definition, okay, because I want to play with this, because I'm going to show you how, a trick to evaluate it. Okay. Okay, so that's z. Okay, and I have fz equals n equals 1 through infinity z to the n divided by n. And if I say f prime z, well, that's going to be n equals 1 through infinity n z n minus 1 divided by n. In other words, it's n equals 0 to infinity z to the n. And that's actually the geometric series, which sums to 1 over 1 minus z if this has a modulus smaller than or equal to 1, smaller than 1, sorry. Okay, so, so this is true. And then we can actually integrate this function to get f of z. So our f of z is going to be minus ln 1 minus z, because this gives us a derivative of 1 over 1 minus z, which is what we found. Okay. I have to keep this stuff around. So, so basically we determined this. Okay. Now I'm going to, okay, I have f of z is equal to minus ln 1 minus z. And this is actually n equals 1 through infinity z to the n divided by n. And then I say f of minus z is equal to minus ln 1 plus z. And that is, of course, n equals 1 through infinity minus 1 to the n z to the n divided by n. So the signs of these, the signs of the terms in this sum alternate. And I can actually then do the following. I'm going to multiply this by minus and add these things together. Okay, so add these things together. So I get ln 1 plus z divided by 1 minus z, right? If I add these two together, but these ones will assure me that if I divide this side by 1/2, that I'm going to have n equals 1 to infinity, the odd terms in the sum. Okay, so I have the odd terms in the sum. Okay, so basically I expressed, I finished my summation. Okay, so I was able to write the sum in a closed form. And now if I go back to my potential, I see, so here's my potential, that it's actually the sum itself that I just figured out, but it's the imaginary part of that. Okay, so what we can write here is that the potential xy is, well, we have these constants, so, and I have the 1/2, so I'm going to fuse my constants here, 2v0 over pi. So it used to be 4v0 over pi, now I divided by 1/2, but here I'm going to have imaginary part ln 1 plus z divided by 1 minus z. Okay, and the last thing that one has to realize, well, to actually finish this problem, is that if I have a complex number, okay, so let me write, okay, for example, if I have a complex number r e to the I phi, if I take the imaginary part logarithm of that complex number, that's going to be phi. Okay, and remember that z is some complex number. So this is our definition of z. Okay, zz, sorry, I used that interchangeably. E to the minus n pi y over a, e to the I n pi x over a. That's z, okay? So basically, the last task is to calculate 1 plus z over divided by 1 minus z, this complex number, okay? And calculate the phase of that complex number, okay? Calculate the phase of that complex number. So let's do that. It's not particularly hard. Okay, so I'm going to, well, we can take this to be r. So let's say r is equal to e to the minus n pi y over a. And well, no, sorry, that's confusing because here it meant something else. Sorry. Yeah, okay. Well, let's do it like this. So I have this term 1 plus z, 1 minus z. That's a complex number. Okay, that's actually a complex number. So it has some real part plus some imaginary part. Okay. But what I'm going to actually do is to multiply this by 1 minus z star, 1 minus z star. Okay, because then I'm going to have a denominator, which is going to be a real number, and then I only need to worry about the numerator. Okay, so so I'm going to have in the denominator, I have a real number, so I don't even need to worry about that. That's real number. But here I'm going to have 1 minus modulo squared. And I'm going to have also plus z minus z star. Okay, now I go back and I use my definition of z to find out what these things actually mean. So I have here, so the important thing is, what is z minus z star? Z minus Z star is, well, it looks like it's e to the minus npy over a, e to the I n pi x over a, minus e to the minus I n pi x over a. So in other words, you can write this also as e to the minus n pi y over a times 2I sine n pi x over a. Okay, so one important thing to realize is that this z minus z star is actually a purely imaginary number. 1 minus modulo squared has to be a purely real number. So the phi, so the phase that we are after is actually the arctangent of this, well, it's not the purely imaginary number itself, but it's the imaginary part of that. Okay, so it's actually, so here I would have e to the minus n pi y over a 2 times sine n pi x over a. Okay, and that's the real part. 1 minus e to the minus 2n pi y over a. So that's where we're at. And that's actually, so this phase ends up being the arc tangent of sine n pi x over a divided by hyperbolic sine n pi y divided by a. Okay, so that's basically the full story. Now you just have to put together the full potential. It's a little confusing because this is a small phi and capital phi. I denoted the potential with capital phi. Sorry if that was confusing, but in the end we get 2v0 divided by pi arc tangent sine n pi x over a divided by hyperbolic sine n pi y divided by a. And that's our potential for this system. Okay, that's the full solution. So thank you for your attention.